Hello, I'm Vittorio Paris, a researcher at the University of Bergamo. Before I begin, I would like to express my gratitude for this opportunity and thank you for taking the time to attend the conference. Today, through this presentation, I would like to share the research conducted in collaboration with a group of Prof. Sigrid Adriaenssens and the SOM studio. The research culminates in the robotic fabrication of a full-scale bolt prototype at the Anatomy of Structure exhibit that is hosted in the Ambika Gallery in London. The structure has been built using glass bricks and epoxy putty. The vault is about 2.2 meters in height, 2.7 meters in width, and 4.4 meters in length. Its shape was obtained through a four-find approach, and it has been built using only two robotics arms and by avoiding the use of any scaffold centering on temporary supports. Hence, it is critical that the vault must be able to achieve a self-balanced state during the construction work. Two, self-balancing historical technology have inspired the construction technique adopted, the pitch vaulting technique and the herringbone one. The pitch and vaulting techniques, also called the Nubian technique, is the first or among the first self-balancing methods developed. To understand how the pitch and vaulting techniques allow building a structure without centering, it is essential to first visualize a barrel bolt under construction. Thus, starting from a fixed support, the bricks are laid readily to form inclined arches placed one next to another. In this manner, during the construction, each arch rests over the previous one, which is already completed, allowing the vault to be constructed without centering. The second technology, the herringbone one, tie or interlocks the bricks of different courses. In our project, these technologies, combined with the use of epoxy putty, enable the possibility to achieve a self-balanced state, and thus to build a structure without any supports. Taking this into consideration, the focus of the research presented here is the evaluation of the state of the vault concerning its construction. From a building point of view, two macro phases were defined. The first phase related to the construction of the central arch, and the second phase, which starts when the first bricks of the second arch is laid, and it ends when the whole vault is built. Static graphics analysis were performed to observe the variation of the arch during the first phase. Meanwhile, for both phases, numerical analyses were executed. Since the early stages of the study, we observe an interesting relation between the form and the construction phases. Indeed, the shape obtained through the form process, here in orange, is quite different from the line of thrust required to achieve a balanced state to the central arch. Thus, to achieve the possibility to build the structure without any support, it is necessary to add an additional boundary constraint in the form-found process. Such boundaries takes into account the variation of the balance during the construction. Even discrete element analysis have been performed to assess the state of the structure. Through this method, the glass brick vault is described as a system of rigid bodies. According to the numerical method implemented, the interface of rigid bodies are rolled by more curved model with a tensile cutoff. Hence, the discrete element can slide, rotate, collide, or even detach. These numerical analyses have been adopted for predicting the displacement of the bricks during construction. The placing of each brick is simulated as its influence on the structure already built. As mentioned, during the first phase, the two robots work together. One supports the portion of the arch already built. The second one places a new brick. Thus, starting from the base, the bricks are laid one next to another until they reach the opposite side. Due to this peculiar construction process, a variation of displacement related to the placing of bricks has been observed. Under construction, the arch slightly swings with a maximum display about 0.005 millimeters. In correspondence with the central arch, 8 checkpoints, the centroid B1, B2, B3, and so on, placed at different heights, were assumed for recording the displacement of rigid bodies during the construction of the whole wall. These measures have been used for tracing the surface of displacement, denoted with zeta, which describes the variation of the position of the 8 checkpoints with respect to the all construction stages. The surface zeta shows the presence of peaks and valleys in correspondence of the second phase. Here, the maximum displacement recorded is one order bigger than the one of the first phase. Despite that, the geometry of the surface confirms the stability of the four-found vault. Further, zeta shows that when a new arch is completed, denoted on the surface by the label second A, second B, and so on, the magnitude of displacement decreases. Indeed, when a resistant substructure is completed, it allows a redistribution of the forces. Consequently, the overall behavior changes, reducing this displacement recorded. The research presented shows the potential of historical construction techniques adopted within the context of emerging innovation, novel computational profiling approaches, and using robotic construction technologies. We want to highlight that the knowledge of the structural states under construction is crucial to building a structure without centering. Only through studies like this, possible failures can be identified. Therefore, the analysis and the discussion reported in this research are extremely relevant to the field of contemporary surveillance technologies, and for drastically decrease the use of new material for construction.